This video is about Beer's law, which is a way of using light to make quantitative analyses of solutions. When light passes through a solution, some of it gets absorbed, so not all of it is transmitted. So in this schematic here, we have a light source that's shining out some, looks like green light, and it goes through a sample of some red material, and on the other side there's not as much light. That's kind of meant to be illustrated by the thinner line there. So the light detector that's on the other side would detect less light than if the sample wasn't in the way. By comparison, we can make a kind of a measurement of how much light got absorbed. First of all, just detect how much light comes through if there is nothing in the way, if there's no sample of material in the way. That's called I0. Then put the sample in the way and do it again, and your detector detects a smaller amount. That's called I. So we can make a ratio that's called the transmittance. It's like the fraction of how much light was sent out by the light source that actually made it to the detector. So what we're measuring here is how much made it through the sample. Here are the things that the transmittance depends on. It depends on which wavelength of light you shine at the sample. If the wavelength of light is about the same color as the sample, it's not going to remove very much light. It's going to pass right through. If it's the complement of the color of the material that you're shining it through, it's going to remove that at a higher rate. It depends on the solute. And this is almost like a restatement of what I just said. If you are fixed on having like green light in this example, a green material is not going to absorb anything, but the complement of green is kind of red, so that is going to absorb some of the light. It depends on the path length. If the particles of the material that's in the solution are absorbing the light, and you allow the light to go through more of those particles, it just makes sense that it's going to absorb more of the light. So the transmittance would be lower with a longer path length. And it also depends on the concentration. If you have the same path length and the same wavelength of light for the same material, if you have a more dilute solution passing through that path length, it's going to encounter fewer molecules than if it passes through the same path length but with a higher concentration of molecules. And so the higher concentration is going to absorb more of the light. This guy named August Beer studied how transmittance varied with concentration. And here's what he found. He got this relationship here. And if you look at it, you can see that there's a slight curve to it. That curve is made more apparent when you put a best fitting line to this data. And you can see that it's not random, but there is actually a slight curve. It looks kind of like a hyperbola, but here's what he found, that it actually followed this pattern. If you have a graph of y equals k raised to the x power, if k is a number that's smaller than 1, then this is going to be the shape of the graph, and that's what he found. Now, if we take the log of both sides, we will get something that simplifies down to x log of k. Now, the log of k is going to be a constant number, and so that means you have a linear equation. So that equation would look like this. If you had the log of y on this axis, and you had the log of k times x on this axis, you would get a straight line relationship. Going back to Beer's plot here, what he has on the vertical axis is transmittance. So that's log of transmittance on this axis. And on the horizontal axis, he has concentration. And the log k is going to be the slope of that line. So he has a way to make a nice linear relationship if he takes the log of transmittance. So what he does is he takes the log of transmittance, which is that number, and he assigns that to a quantity that he calls absorbance. And remember, that's on the vertical axis. That was the log of transmittance. And concentration is on this axis, and this gives us a straight line. Now, why does he take the negative of it? Because he just wanted a positive slope. That's what it comes down to. So he changed it from log of transmittance to the negative of log of transmittance. So there is a straight line relationship between this quantity called absorbance and the concentration. This is an example of what's called a Beer's law plot. It's that absorbance versus concentration graph. And what this is valuable for is if you have known concentrations, you can make this plot. And then you can use this plot in reverse to find out what is a concentration of an unknown solution. So you can use this equation, absorbance equals 15.25 per molar times concentration, to find out an unknown concentration. Or you can just read it off the graph. So let's say our absorbance was 0.5, and we wanted to know what concentration that corresponds to. Just read it off the graph. There's a slightly more expansive version of this called the Beer-Lambert law. So we know that absorbance is proportional to path length. So we can take absorbance equals constant times concentration, and we can now imagine that that constant is going to be made of path length and some other constant. And that other constant is called the extinction coefficient, or sometimes it's called the molar absorption coefficient. So that value given by the Greek letter epsilon, that depends on the particular substance that you have. Different substances have different extinction coefficients. The path length, well, that's going to depend on the particular device that you're using to make this, and then concentration, of course. So this is just a more expansive version of Beer's law, called the Beer-Lambert law, that accounts for path length and for a constant that's related to the substance that you're analyzing.